Good morning. Okay, so as usual, I'll start reminding you what it's all about. Even though it's always the same. So, but at some point it will diffuse in. So this whole course is essentially about the quantity, let me write an example, corner, which is an average logarithm. So that's the main formula. And it's 90% of this course. About this formula, it's motivation, it's generalization, aren't that far. One of the ways to look at this formula is to say that this is the only formula which satisfies the subdivision rule. So let me tell you, I'm looking for a function of n numbers the sum of these numbers is unity, and I impose on this function the following property. It's called subdivision, which is a fundamental thing of what we are doing. It says that I can take it as a function of n minus 1 numbers. One of way of doing it is that I take p1 plus p2 as a single number. It's also less than unity. All p's are positive. p3, pn, and add to it the following quantity. The meaning of this formula, is it clear? Just meditate a bit on it. Well, it's a requirement, right? So I want this function, this is an equation, a non-trivial functional equation of a function. It's iterative. It expresses function of n variables through the function of n minus 1 variables and function of 2 variables. What is the meaning of this formula? How would you explain it by words? Yes?
Two states collapse.
Huh?
Two states collapse to one.
Well, I don't know what you mean by collapse. I mean the probability ends to 1. This is a measure of uncertainty of this distribution. It's also a measure of a surprise when we given any answer about what actually, which object appeared out of it. It's an average degree of surprise. Or you can say that this is something which is just measures how much uncertainty is about this distribution. It tells you your full uncertainty of your distribution is your uncertainty about this distribution when you don't distinguish between 1 and 2. You treat them as a one composite object. You remember when we were decoding and doing Huffman code, we treated A and the GTC as just one composite object, right? So what it tells you, it's your measure of uncertainty without distinguishing 1 and 2, plus your measure of uncertainty of distinguishing between 1 and 2. You see, this is the relative probability of 1 in this pair. This is the relative probability of 2 of this pair. this formula, which derived by mathematician Hinton in the 50s. And as this formula, that's Gibbs, that's 19th century. And treating it as information was 20s. It took 30 years to realize that this is the only solution of this equation. I'm not proving it, but I mean, you're welcome to spend some time at least thinking how would you prove it, right? Etc. So this is essentially this beautiful mathematical statement is an expression that incidentally you can also prove that it's convex, all the bells and whistles. Okay, so this is so now when we are talking about language after that, so what we were discussing is that of course we can write it alphabetically and we can use it for 26 letters plus 6 samples as a 32 alphabetical and syntactic signs. And so if we would say that the only thing that we know that there are 32 n is equal to 32 different objects, and we don't know anything about the probabilities, which means that each one we can assume one of it divided by 32 as the same, then we would say that this measure of uncertainty would be log 2 with 32. Log 2 means we measure it in bits, and bits are number of bits is a number of yes-no questions or answers to yes-no questions. That would be 5 bits. And then I told you, I think, a fantastic story about Samuel Morse and the first telegraph as the first encoding of language by a binary code. And what we realized that if you now look at this formula with the probabilities of real letters, right, that the probability of E is 0.13 and the probability of Q is something like 10 minus 3 in English language. Then you compute S of P's, that would give you something like 4.2 bits. Okay, good. So now you say, look, now I am in 21st century, you know, I want to transfer just, you know, not teras, I mean just we transfer terabits per second for, you know, for a single building, right? So I want to compress it as much as possible, right? And that's the whole idea. And then we have this formula which tells you something how this is related to the average length of the code word. So if you encode it in bits, that would be larger than S of P and smaller or equal to S of P plus 1, which means that we can now do what Morse did. You can encode this by a dot, which is a very short code word, and you can encode Q as very long code word, right? I don't know, even 5. And then on average, you can try to reach all this. But the first telegraph, which was British telegraph, really, working on an industrial scale, namely on a country scale, was even more efficient. And which means that it made all the messages even shorter than 4.2 bits per letter of alphabet. And how they managed to do it? How would you do it?
Take into account the connections between letters.
Yeah, and how would you do it?
Take into account the probability of common words.
So you know probability. So how would you? I mean, you're working with Morse, right? There's still, I mean, for another 100 years, nothing better than this painter invented. You know, just you know. But so what you would do really?
Look at the pairs of letters and not a single letter.
So you know probability. What would you do? I mean, you're a businessman or you're an engineer, right? You really want it short. shorter, you do something simple and it works, which is. That's how you do startup, yeah, that's right? So at some point you realize that you can do something and it will be cheaper. Good, okay, so you can beat everyone else. How? Because you know something about probabilities of different letters, namely correlation between different letters. So you know correlation between different letters. They suggest that what next letter will be. So what would you do? I'll give you 1 minute to get your first $1 billion. That's a $1 billion question, right? We're talking, a country scale telegraph.
You don't write all the letters?
You don't use all the letters. You just drop some letters. They don't exist. Because if this letter is missed in a word, you can guess it because there is correlation with other letters. Okay? So what would you drop if you are English person? Well, definitely you would drop Q, right? And why you would drop Q?
You can use K.
Huh?
You can use something else.
CK also, apparently you can kind of use only one of them. But Q is particularly atrocious in English language. It's straight from Latin, and the
I said that you can drop the U after Q.
yes, you already ready for your first $500 million. So there is a thing which I now introduce. It's called conditional probability. That's precisely what you suggested. There's something which explains you that some letters are more probable after others. This is a correlation between neighboring letters. And one of the things is that the probability of U after Q, that's how I would express it, right? So probability of U, conditional that you have put, is 1 in English. All U always goes after Q. That's it. There are some proper names of, foreign kings that, but generally, and this actually follows from all these quorums, and it's late. It's just something which is deep inside English language, which is of course barbarian language from, some Germans, etc. It's still some Latin is encoded inside in the alphabet. Okay, and so now let's talk with this conditional probability and see how much we can lower the entropy or how much we can shorter our average code word sending this symbol. Incidentally, they also dropped in the first telegraph, they brought C, J, Q, U, and X. So they don't even use this, they just drop them all together. Okay? So, and of course, this is based on this general idea of conditional probability.
Do they do something instead?
Huh?
Do they put in something instead, like a dash or something?
They put something instead, they believe in the customer common sense. And it worked.
But you have like words where if you drop both Q and U,
Okay,
you just get
let's
different ones.
let's
So,
check. Yeah, I already wrote it, but let me do it again because again it's a famous posting from New York subway. So where is it? It's also part of a poem. That's clear. It's if. It's clear what is this?
How?
It's you. Okay, so let me write it all and then we'll try to read it. This is from New York subway, circa 72 probably.
If you can read this, you can get good job.
This is really important. Okay? So this was a poster in New York subway, and so if you Google, you find a poem, and which is it's a part of this poem about megapolis. So if you see instead of, so what I am doing, it's called non-traditional grammar, and your people know this much better than me. You are texting, you are texting generation, right? Which means that you use this all the time, and of course, it's only in 21st century. I mean that also you are overeducated. Can read 2 instead of 4, right? This, you,
I thought that's a Z.
if you can read this, not that,
No.
because it's S.
No, the read.
No, the
yeah,
R when you
R
grow,
for the
it
read.
looks like a Z.
Sorry, it's D, yeah. It's D.
The
V wasn't for R.
Huh? If you can read this.
Okay.
So what's it? Okay. You can get a. What else could be? You can get a, of course, good. If it's good, then it's job, right? What do you would expect to see? You see advertisement in the subway for buy something or job postings. With high
Payment.
pay. And as we, again, not a problem, all of you. So it's advertisement for a secretary job. It was really a good pay. Back in 70s, somebody who can read this can be a secretary. Okay? Can really hear what this boss mumbling and and do a perfect text out of it. Okay? So now if you look at this, you find out that this is approximately 3 times shorter than the whole version of it. Right? Which tells us this important thing, that probably real entropy is not this, it's much, much less. Let's compute it, okay? So now, when we understand that you can know something and you know would be inside, because C and N are very much correlated with what is inside here, right? So now,
But you also use the knowledge about the context.
you read the note, of course. Here it's a much, much more, which means that for now, we'll just make a first step, and Claude Shannon did all the other steps. So what we now need to do is to say, okay, look, I now know this, which means that I know P of J going after I, and Ij, they all run from 1 to 32, so this is all our alphabet. I know all this. It's a matrix now, okay? So I need to give 2 numbers to give you an entry of this matrix. And it now comes instead of this vector. That was a vector. This is now matrix. Which one contains more information about length? Why?
Dimension.
Well, matrix is n by n, but still maybe just some things are related. But it's only matrix one way, which means, first of all, it's a probability distribution with respect to which
J.
J. It's a probability of having J. It means it's the sum over J of P, J, I equal to unity for any I, right? It's called such matrix, and we'll meet it when we discuss Google page rank. This is how Google get their first $1 billion. This is a matrix called stochastic if all entries are positive and every column sums to unity. What it tells you that when you sum every column for every row, yeah, you just take and you sum, so every column sums to unity. So now, what we would like to do, we would like to do the same game that we played with asymptotic equipartition. Namely, we take something like I at position 1, I at position n. So we have a very long sequence, a telephone book. Okay? And we would like now to understand, we can of course look just at this long sequence and just count how many different letters are there. This would give us 5 bits. We can look at the probability of different letters. This would give us 4.2. Now trying to play your game. Namely, let's now look at the same sequence and from it compute also probabilities of pairs. Okay? So I just look at a given A and I ask what is the probability of A after A, B after A, C after A. That would give me this. Okay? Now you suggest that this matrix has more information than this vector. But they are related or not. For example, if I know this matrix, could I find this vector?
Yes.
How?
Get some.
Yes, this is the right beginning. So what I can sum? I cannot just sum it. You see, this if I sum it over J, it would give me 1, right?
Sum it over I.
Huh? Of course. You see, it's called condition of stationarity, which means that if I take P of P of J under condition of I, right? But I need to sum over J, but with the probability of every J. And that would be a probability of I. Right? It's called stationarity, which means that there is P here and here, right? But it's an equation on P. Or, because you are overeducated people, this is a condition that the vector P, how it's related to the matrix Pij.
Eigenvector with eigenvalue 1.
Absolutely. It's eigenvalue, which means that, of course, matrix contains information about all its eigenvalues. This vector of probability is only highest, and then, of course, and I'm not giving you all this beautiful science, it's called Fred-Golm, Markov theorems, etc., that every such stochastic matrix has eigenvector which has eigenvalue unity, and this is its largest eigenvalue. You cannot have more, but in a month I'll tell you how Google made their first $1 billion out of this theorem, essentially using this property of. Now such matrix defines what is called Markov chain. And Markov chain, it's a stochastic process in which a next step completely determined by the previous ones in terms of probability. Namely, if you know a given state, you know what are the probability of the next letters. It's exactly this matrix. Okay? So now good. So now I know that if I know this, I can find the eigenvectors, etc. So now I would like to estimate the probability of this very long sequence generated by this Markov process. So now our typical sequence is called Markov chain. Or you can say that there is a Markov source which generates you letter after letter with this probability. What is the probability of this given sequence?
Probability of the first times the condition.
Yeah, so first of all, the probability of y1, yi, yk, yn is the probability of y1 standing on the first place plus you need to say that this is a probability of, you need to, it's a product, right? So you need to take the probability of y2 under condition of y1, multiplied it by the probability of i3 under condition of i2, and of course, some, I mean, overall, so you know all these numbers, you just need to multiply this probability.
Isn't it a product also at the beginning? Like no plus between pi.
Yeah, this is a product.
No. Left of this. Like it's not py1 plus. It's a py1.
No, it's a product.
No, left of this. Like the first.
Oh,
Yeah.
Yeah, a product. Sorry. Yeah. Okay. So you take a probability of a first. Well, it literally that's what they say that all this probability theory is Hebrew because you always read it from right to left. Okay. So now you go the probability of y1 times this transitional probability times this transitional probability. But you want to estimate it like exactly like we did, which means that that's what we look at. We look not at probability, but at
Entropy.
how entropy appears at all. So you want to estimate how this probability. If somehow a probability decreases with n. The larger the sequence, the more are sequences, and the less the probability of any given one. So essentially, you're asking how many different sequences. Then one over this would be how decreases the probability of any given such typical sequences. The only difference that before you had independent numbers, so it was P1, P2, P3, P4. That's what we did when we did asymptotic equipartition. What's now you have instead? You have not P2, but P2 under condition of 1. Not P3, but P3 under condition of 2. Okay? But it's still a problem. But now they are deep. So what
So for Markov chain, it doesn't go deeper than one step back.
Markov means one step. That's the definition. There are generalizations, but they don't call Markov. Okay. Markov was 1906. There was Russian mathematician. I mean, this the whole idea appeared. Okay. So what you would do?
Log?
Huh? Take log. I mean, all. I mean, when I ask what will you do, your first reaction must be take a log, and then you start thinking maybe it's a negative number. So it's positive number, right? So you take a log of it. So you take a log of probability, and when you take a log of this product, it would turn into a sum. And now we can use the law of large numbers, saying, okay, if I have a very large sum, then I expect it to grow linearly with a number of terms with a rate which would be an average value of each term, which is an average value of a log, which is entropy. But it's a different entropy now, okay? Because what would stay here, that would be log of P1 plus, let me write it as a big sum, plus the following one. So you sum it over k from 2 to n, and what stands here is a log of probability your letter, well, I would yk plus 1 under condition of yk. Okay, so this is your formula, and now you want to say what would asymptotically it would be, and you expected that would be totally irrelevant. It's a huge sum, right? And so it would be, of course, now this is negative, which means that it would be a very, very big negative number, because we're talking about probability. Probability is very small, but see, still big negative number is much, much more negative than all this. So you would expect it to be minus n, and that must be some entropy here. An entropy is, by definition, is a factor which stands in front of n. The question is what entropy? Of which probability distribution?
Can you explain that again?
What I'm saying is that you have a sum. There is a log. What you expect that when n goes to infinity, let me write it in a little bit. That would be times average value of log p yk plus 1 yk.
Can maybe plug in a base.
So there is a probability. This is a probability distribution. This is log. Okay? And the thing is that, as usual, your rate of decrease of your probability or increase of the number of typical sequences is an entropy of distribution. But this formula tells you that this is an entropy not of your distribution P1, P2, P3, but the distribution of conditional probabilities. Okay? So what stands here is a sum over J of P of J over I log P of J over I, but it's not enough because at every position I could be different letters, so you need to sum it also over I over different PIs. And this is called S conditional entropy. Okay? And this is something which lowers your, if you compute it, just take any book, compute it for English language, it brings you down below 4 bits. And then, of course, you can do it assuming that you now not have a Markov process, which is a one-step pony, but you have a two-step probability, etc. And then, of course, you can do it even better, namely, this is what is now AI gives us perfect ability to do. You can just ask people or your AI trained on it to predict the next symbol. Or you do what I did with this thing, which essentially Shannon invented. You wipe out some letters and you ask people to restore it. At some point you realize that when you wipe out 2/3 of it, people stop predicting it. And so eventually it all comes down approximately, if you do it with symbols of 1.4, if you do only letters. Which means that for letters, log 26 is 4.7. So you go from 4.7 to 1.4 bits. That's a true entropy. That's how many letters you really need, or you do other encoding. And sometimes it's expressed by stating that the redundancy is factor 3. Okay, which means that, and of course, it's now enormous body of speculation, and even some science appears why we invented alphabet, which is such a redundant way of encoding. Well, maybe now just enough formulas. I'll try. I'll maybe spend this last 5-10 minutes on. Just I want you to feel all. What is this, right? First of all, what is alphabet? You know that alphabet was invented only once. Only once in mankind, and it was Semitic alphabet, incidentally, right? There are many other encodings which were invented independently. Before alphabet, what we had?
Symbols.
We had logograms. And logograms mean one word, one symbol. Because the unity of meaning in language is a word. So it's a very natural to encode meanings. You know, I go. I is a symbol, go is a symbol. To school, to is a symbol, and school is a symbol. Now, I mean, just look what these people did. They took sound, somehow broke it into what we now call phonemes, okay, and encoded those phonemes. Phonemes in a language are tens, like 20, 30, 40. So instead of like 5,000, I mean, a normal educated Chinese knows 5,000 symbols, right? So before alphabet, only a very small elite, educated elite, could learn writing. A moment you need to learn 20 symbols and not 3,000 or 5,000. It's a huge democratization of knowledge transfer, right? But it's extremely poor. Nothing in, I mean, if you listen, for example, I mean, my second son, his wife, I mean, she is a linguist. And they have the, I mean, he is a former mathematician and now neuroscientist. So they have a together project on poetry and how actually people hear and how people recognize it, and also how people recognize when this word ends and the next word starts. And then you recognize that French and Germans do it differently. Absolutely. I mean, just listen to how French speak. And of course, people hear this rhythm and endings, and so it's a very, very complicated thing. And then we invented very short and very poor encoding, but we invented it with huge redundancy. And this number tells you how redundant it is, because this redundancy, first of all, it protects against errors, right? So if in the text, or you don't really hear it very well, but you have this correlation which helps you to restore, right? But there's something probably more to it, and yes.
Is this factor similar in different languages? I mean, this is in English, but
Very good
we
question.
check it.
I'm sometimes regret that I went into physics, because now is an epoch of linguistics, right? Because there's now AI. I always dreamed of having all the conditional probabilities, and now you can have it. You can just ask, you Claude, which named after Shannon, right? And he will give you. So now it seems that redundancy is essentially a little bit higher in older languages, okay? But generally, alphabets more or less between 2.6, 3.1, usually a little bit less than 3, but all the same ballpark, right? So one of the things in which we'll talk on the lecture maybe month and a half after it, where we talk about brain research and what is called active inference theory, is that how our brain actually works. And our brain, the idea goes back to 19th century, but now we have experimental, more or less, support for it. Our brain works as a predictor. It always predicts and compares predictions with what he obtains. For example, if you put a person into a dark room, which means that there are no photons hitting the retina, and then you switch light and the signals start coming, and you can measure how many signals go from your retina to the brain and how many signals go from a brain to retina before you start seeing something. It's comparable number. So our brain always predicts. And because it's always this predictor corrector thing, he needs this kind of support. And so he does it. And it's all probabilistic. It's always probabilistic. There is a, you probably read, if I don't know how your generation is this, Lewis Carroll, Alice in the Wonderland, some of you, right? But there is even, that's for kids, and for adults he has what's called Hunting of a Snark. It's a beautiful poem. And the refrain there, which I understood like 30 years after I read it, is like, what I tell you 3 times is true. There is a captain in this boat, and he says some things, and some of them are lies. But if something appears in the 3rd time, this is truth. And Lewis Carroll, as you probably know, he was a mathematician in the 19th century. So this is something which he understood very, very intuitively. Our brain works like this. If you hear something for the 3rd time, that's probably true. The 2nd time, the jury is still out. Okay? So, genome. What is the redundancy of a human genome? What we encode by these 4 letters, you remember this? There are 4 letters. Okay? So if you, I guess I call it m equal to 4, right? So you have 4 letters. And we have about 20 amino acids. Okay? So apparently we cannot encode by 1 letter 1 amino acid. Not enough. How long we need to have a word made out of this? If we take 2, how many two-letter words made out of 4. 16, right? So there is can be 4 here times 4 here. It's 16. Still less than 20. So what nature does, it uses triplet code, right? So how many such words? And it's 3 times more than the number of amino acids. I'm not doing any speculation here. This is just how nature works. And of course, this is again protection against error. Errors here are little, right? And again, it's very often that one amino acid are encoded by different words because we now have redundancy. And these usually words which are different by only one letter, right? So that an error in one letter won't lead to the change of it. But then again, nature had its own Samuel Morse, which means that some amino acids are more frequent, so you use more ways to encode it. You protect them more, right? But the average degree of redundancy is 3.
So it's
in
kind
the
of
genome.
as redundant as
64
language.
divided by 20, approximately 6. Again, we'll talk over and over about this fantastic similarity between language and genome. Even though it's clearly of very different origin, but some things are really very similar. The most important is that it's really very well protected. So this is a way of transfer information. Both are way of encoding information, right? Both are very, very good. And the most important part of it is that potentially infinite. Right? So you can, in one virus, there are that many the things that the number of combination is about order of atoms in the universe. Which means that we are not even started to explore the whole kind of all the possibilities given. And of course, language works it in an iterative way. We create new words, but it's a relatively infrequent process. But we can create new sentences and we create meanings out of this new stuff, right? Okay, so good. So let's make a break, and in 15 minutes we'll go over. Questions? Any questions? Everything is clear? This must be moving. Okay, so what we now do, we'll move forward and we'll introduce today next fundamental quantity, which is generalization of this formula. But it follows from the same, namely that we now have a new instrument, and this instrument is not just probability distribution, but conditional probability. And so we just have entropy, we have conditional entropy. So let's see how we can use it in a very, very universal and general settings. So now what I want to do, what I'll be doing now, I'll be doing communication theory. And so the language will be that of source, receptor, channel, which is between them. But it's a very, very general setting. Well, I already mentioned it in the previous lecture. So if you're experimentalist, you can think about what you measure, I mean the objects that you study, I mean your cell or your crystal it's a source. What your device, your measuring device show, it's a receiver. That's what you actually receive. So all the process of measurement you can treat as a channel in communication theory, right? And so the main question which appears in the theory of communication is how good is my channel? Okay? So that's what you want to ask. So essentially, we now treat everything. If you're a theoretician, the same thing. You make prediction about something, right? That's your kind of message that you receive. And there is this something which experimentally somewhere will measure, right? So now you are asking, how good is my prediction about what is there? It doesn't look like communication, but it could be treated in the same way, right? So the formally, and that's something which I will be using over and over and over again. That will be, of course, Bob and Alice. It will be when it will be in a quantum communication, but it will be B, which is the source, and A, or you can say input output. That's what you have. That's what you are interested in. Okay? And generally, you assume that what is called noisy channel. So what the Claude, not AI, but Claude Shannon did, the first he proved the theorem which I just erased over here, about entropy being the maximum rate of communication, and second he proved noisy channel theorem, which I'm not going to give you the theorem, but I'll explain you what it's all about. So it is something about that you have B, and there are different values possible of your input. Let's say you have 10 to 23 position of an impurity atom in a crystal. Okay, and then there are different AI values. It could be 10 readings of your device. So they live in a totally, different spaces, right? So here's the probability. So generally, there is something which you don't know. There is probability of different BJs, and it can live in a very, very large space. And then there is, of course, the probability of it, but you aren't really interested in the probability. You're interested in how much you learn from here about this. And this is characterized by what? What is this characteristic that you're looking for? We say, okay, look, I measured a given value AI. What I want to know, what are the possible values of BJs, and what are the probability of these possible values? So what characterizes the channel is the conditional probability of every BJ, some of them are zero, under given AI. Right? It's a conditional probability with respect to what? The sum of a what is unity? B. Which means that the sum over all J, P of Bj over AI is unity for every I. Like we had it before. I'm just using the quantities that we already used. So now, it's a probability, and for this probability, again, exactly like I just formula that I erased it intentionally because I now want to write it again. I can take the logarithm of this probability of Bj under given AI. It's a probability with respect to.
Sorry.
So you multiply by the probability, by the same probability of AI, right? So you sum it over J. And then, of course, you take the probability of AIs, you sum it over I's, you take minus, and you call it conditional probability of having B under A. Right? That's what you expect is really characteristics when you perfectly know for every A what is B, what would that be? When this guy is delta function, is delta symbol, namely for every I is just with a probability 1, you would get,
Zero.
then it's 0 because all the logs are 0 over here. For every I you have probability which is 1. Which means that, and there is no uncertainty about B, this is 0. So this measures what uncertainty about B when you measure A on average over A's, right? Okay. So this is essentially how much uncertainty remains after you did measurement. Okay. How would you expect it to be comparable with S of B without any measurement? This is bounded by this. If there is no correlation between A and B, this is P of B. That does not matter. And I get back to mine. Which means that I expect that if I do something and measure something which in whatever way is correlated with B, maybe imperfectly, I would diminish my uncertainty. Okay, good. So now, what I would like to ask is how much information I can transmit on this channel. You remember, before I erased it, so let me remind you that we had this P of Ji, and we take a log of it, and we take a P of Ji, and we sum it with Pi over I and J, right? And that was the information rate per unit letter with a minus, right? Or the total number of sequences was 2n to s, and the probability of n sequence was 2 minus ns. So in this case, this conditional probability of Ji, namely next letter after the previous one, sum over all possible pairs, that would be how much information is in my n sequence. Because it's exactly the amount of information per letter divided by n, right? But now, can I just take this and say, okay, this is how much information I will get out of my measurement? Could I just say, look, okay, this is a conditional entropy. This conditional entropy tells me if I have a text and I just look at probability of pairs, then the average entropy of this distribution is my rate of information transfer per letter. Now it's something idiotic if I say that this is, because then I would get maximum when there is no correlation between A and B. It's something wrong. So what is a characteristics of how much information on average I receive out of measuring A?
Maybe it's like the error probability?
Error probability would be what you call error. I have the whole distribution. So for every A, I have B appearing with different probabilities. But you have only 10 readings of your device, and for every reading there is a vast, part of your crystal where your impurity could be. What you would call error.
Error is if I isn't equal to J.
Well, it should be. It's in a very, very, so you're now treating a legitimate but very particular case where what I have, A is just a scrambled B. Namely, I was sending letters and some letters came as they should and some letters would just, because of noise, would turn into something else. But I'm treating it in a much more general setting. This could be a space which is very different from this space. This could be, three-dimensional position of an atom, and that could be just 10 letters, 10 numbers on my reading device. This is a very, very general setting. There is no kind of easy way. But what is information generally? If you explain it to your grandma, how you'd explain to grandma what is information? How you can quantify it, measure it? If you can't explain it to your grandma, you don't understand. Okay? That's general. That's what I learned from my grandma.
It's the reduction in uncertainty.
It's a reduction in uncertainty. So, what is the reduction of uncertainty reached by this measurement or messages?
It's just the entropy because it's zero if it's uncorrelated.
It's a reduction in uncertainty. Reduction in your money, you look how you have money, and then you see how you now having money. Aha, that's a reduction. Okay?
The difference in the
Reduction is the difference in uncertainty before the measurement and after the measurement, on average, after many, many measurements. But per measurement. Yeah? So what was my uncertainty about B? Before I did any A's? S or B. Good. So that's my initial uncertainty. And what my uncertainty after I did the measurement?
That's the condition by.
This guy. So the decrease of uncertainty is this. And as somebody already helpfully said, that this is generally bounded by this, right? So you cannot increase your uncertainty, right? The maximum they are uncorrelated, right? Which means that this is non-negative. This is the next most important characteristics, this conditional entropy. It's called mutual information. What should I write here? This way, or this way, or that way?
That's one.
This, or this?
The last one.
The last one. Writing it as the last one immediately means a very strong statement.
Symmetric.
It's symmetric. Do we expect it to be symmetric?
Yes, because we expect it to be a characteristic of the channel and not of A or B.
Yeah, but channel goes
Channel
one
could
way.
be-
Channel goes one way. Which, let me put it in a most dramatic form. So I'm having 10 readings of my device and trying to get something about 10 to 23 possible positions of my atom. Let's say I know exactly the reading of my device. Does it tell me the same amount of information about position of my atom as if I know exactly the position of one of 10 to 23 position of my atom, how much I know about my reading of device? Immediate answer, yes or no?
No.
Somebody thinks yes? Name, again, I repeat the question. The information about one of 10 positions give me the same amount of information about one of 23 positions of the atom as an exact position of one of 23 atoms give me about readings of device. The answer is yes. And then what makes it non-trivial, because you see, your intuition fails here. And I intentionally took this dramatic difference just to show you how non-trivial is this statement. Because a correlation is always mutual, right? Which means that if you know the position of atom, it still tells you that in this region, because what matters for my 10 readings of a device is just in which region it is, not its exact position. But let's prove it. Is it understood what I said? Because you say that this is this, and it's true, right? But for this, we need a very simple formula. No. This way. Which is called chain rule, and we'll be, of course, using it over and over and over. So we have generally introduced a quantity which is called joint probability distribution. Namely, if I have B in the position J and I observe A in the position I, the joint probability of this pair is such. It's called joint probability. Now, if they would be independent, right, then it would be probability of AI times probability of BJ. But if they are correlated, this simple product rule, which works for dependent, now turns into what is called chain rule. This equality is called chain rule. Because you can continue like we did, right? So, indeed, the probability of having AI and Bj is the probability of AI times the probability of Bj under condition of AI. Okay, good. So now let's look at this formula, which is sum over P of Bj logarithm P of Bj with a minus, right? And minus sum of a P of AI, P of Bj under AI, logarithm of P of Bj under AI. Yeah? Do you agree? Of course, I can always write this as AI and sum over J and I. Just summing over I, we just leave it P of Bj. And then, so this is minus and this is plus because I use a minus here. And what stands here? According to the chain rule, joint rule. So what stands here, again, Rji, is probability of AI Bj. So I can write all this formula in the following way. It's a sum over, I would write it without a minus, Ij, P of AI Bj, logarithm of P of Bj AI divided by P of Bj. It is this guy which I put here in the denominator, right? And it was with a minus, so it went down, okay? But of course I can write this guy as this one divided by this, right? I guess you already see, but I'm bringing you. So this would be AI Bj P of AI. And it's now perfectly similar. Okay? Is that clear? Just look at it. Sometimes it means that one can of course write all this. This one is S of A and B with a sign minus, right? It's an entropy of a joint probability distribution. And now this with B, this would be plus S of A plus S of B. Okay? Again, you see that this is symmetric. Moreover, you see that the amount of information that you get from B about A or from A about B is the sum of their entropy minus the entropy of their joint distribution. If there any degree of correlation, this is always less than this. If they are uncorrelated, their probabilities are product, their entropy is the sum. Okay? And sometimes, and some people don't like it, but I know I like visuals. So what I'll give you a visual about it, and it's called Venn diagram. So if you just assume that you have something which is whose lengths more or less characterize the entropy of A and B joint distribution. And then there is somewhere A whose entropy could be characterized by this bar. And then there is somewhere B whose entropy could be characterized by this bar. Again, this could be very small, this could be very large. They're very, very different, right? It could be, like you said, it could be that they're comparable in the sense that A are the same letters as B, just some are scrambled. Just part of it. Okay? But I put it like this shifted, then if I take, and I may ask, what is this, and what is that? So what is this? Huh? Mutual information. This is S of A plus S of B minus S of AB. This plus this minus this. It is this bar, which is extra. But on the other hand, let me remind you that my mutual information can be written as S of B minus S of B of A, right? So this mutual information is S of B minus S of B of A. Okay? That's conditional. Okay? Now, by the same token, my mutual information is S of A minus S of A under condition of B. So that's more or less the geometric meaning of this stuff. Okay? So this is mutual information.
So it's always true that SA plus SB is smaller than S of AB?
S of A plus S of B is always larger or equal than S of AB. Okay? So if there is any degree of it, now why this quantity is so important? Because it's a universal measure of correlation. If you're a physicist or engineer and you would grow like me in the previous century, the correlation means for you A times B divided by A mean times B mean. It was always about correlation function, which was always quadratic. Okay? And this is, as we'll see in the next lecture, is a right measure of correlation only for Gaussian distribution, for which variance and mean completely characterize it. And then already, not when I was a student, but now in this century, doctors come to me and say, and they treat bipolar disorder, and they say, I mean, look, we have the stem cells, and we try this drugs, and we try this drug. We see there is a correlation between this distribution of potassium here, and our neurons work like this. We need to characterize it by numbers, right? And so, what is the right and I look at their distribution, and they not only non-Gaussian, they are, God knows what. It's a very complicated statistical distribution, but they need a number which tells them what is the degree of correlation, and this is a number. Mutual information. This is a universal degree of correlation for any distribution. And then I have a paper in the journal which is called bipolar disorder, because this how, and so this is something which I really want you to remember, and that's what is the importance of this quantity, that this is a universal measure of correlation in bits. If you take log 2 over here, that you say how many bits in A about B. Okay? So you have your self-driving car, you have a camera, that's your A. What is on this camera? What is your B is the car you're about to hit, right? Or your road situation. Okay, so you ask, they usually ask how many bits per second I get. They know how many bits per second are in the camera. It's just, you can count them, how many pixels and all this. But about this B. Well, next month we'll talk about how you can really compress it. Okay? Is it clear? Think about it, ask questions. No questions? Okay, let's do some examples. So again, the most important part here is that mutual information is indeed information, because like you said, information is a decrease of uncertainty, and this is my initial uncertainty minus uncertainty which remains after I got a message or did a measurement or made a prediction or whatever. Okay? That's decrease is a mutual information. So now, let's say I have my B, and there are n values of B from 1 to n, and there is A, but for every value of A, I can get m values of B. Imperfect channel. When I measure A, there still some uncertainty remains, which means that the total number of possible values of A is just n over n. So there is a second one also come out from this. Okay? What is the mutual information between A and B or B and A?
The number of objects in B that A encodes. It's apparently logarithm, right? So what was the uncertainty about B before I know any A? Log n. Right? So S of B is log n, right? That how much uncertainty remains for A. Now I know A. How much uncertainty remains? So this is S of B under A. So if I take this minus this, my mutual information would be log n over m. I can also look at it from this viewpoint. This, what is S of A? How many values of A?
Log n divided by m.
So it's a log n over m. So, but I can also say that my mutual information is not only S of B minus S of B over A, but it's also S of A minus S of A over B. So S of A is now log of n over m. But what is this?
0.
0.
Because
If you know B, there is no uncertainty about it, right? So that's how, you see, the formulas are different. The answer is the same, right? So this is equal to this minus this, and it's also equal to z minus z. Okay? Good.
Now, of course, you can also, maybe let's do this simple exercise. Yeah, first of all, from this formula, what is another important thing is that because, as we say, this is always non-negative, it essentially tells us the following statement. Let me just write it over here. What this ratio, which is essentially, so let me write it's a logarithm of probability of bj over ai over probability of bj, which is the same as a logarithm of probability of ai bj divided by the probability of ai and b probability of bj, right? So I can write always conditional probability by chain rule as a ratio of journal. So what we essentially say that if I average it over all I and j, let me just write it, then this is non-negative. And does it mean that if I don't average it, namely I just look at this quantity for a given I and j, that it's necessarily, positive means that this is larger than unity. Now I'm looking at a given number. For a specific AI and bj, I am asking, this was the probability of bj no matter what is a. This is the probability of given bj for some special a. Does it necessarily larger than unity, or it could be both? Both or not? Does what we say that measuring A on average over all possible measurement, non-increasing my uncertainty about B, okay? Which means that it decreases the entropy, and decreasing the entropy means that this logarithm is sign definite. But this is only on average. Now I'm asking, if the probability of a given B unconditional always larger, always smaller than the probability of B conditional on some specific value of A? Of course not. Yeah. This probability of A maybe excludes this value of B, this particular value of B. Maybe this A value and this be anti-correlated, namely the kind of, if I measure this, the probability would go down, it can go down all the way to 0. This is really important, and one of the problems in the book, which likely could be on the exam, something very similar, it's about precisely this. So you ask about conditional probability of something, under condition of something, because you don't expect it to be larger or smaller, whatever it is. But when you average over all possible events, and that quantity needs convexity. Yeah? You remember that if you just look at this, so if you average, then it's usually something which is sign different. So it's really important to know that this could be anything, but this is always positive. And that's precisely what is written here. Okay? And now what I want to maybe finish, let's consider a counterpart. Is that clear? Think about it. Well, I'm drawing a picture. Think how comfortable you are with the statement that conditional probability can go either way, but conditional entropy is always less than unconditional. It's really important. Okay, now what I want to do with this B and A, I want to turn the tables. Similar, okay? So now I have here K and I have here L of this, and K divided by L is equal to M. In this case, M equal to 3. Well, K is 9 and L is 3. Okay. So now what is the mutual information between A and B in this case?
Log of 3.
Huh?
Log of 3.
Namely, that you just look at this side, like here. You look at this side, it was N over M, that's what your mutual information, because any knowledge here gives you exactly this. Which means that now this is your S of B, and this is exactly S of A minus S of A under condition of B. Okay? So it's just totally symmetric. And now the last thing that we do today is we introduce the quantity with which we'll be working over and over. But let me finish this, just maybe the same statement which I write now in a different form. Okay. So when you average, because this is S of A plus S of B, and this is S of AB. Okay. And the last definition, and then we'll go home for today, is that now you really want to characterize your channel, and then you notice that S of B, that this mutual information is a characteristic not of your channel of measurement. It's a characteristics of how A is correlated to B. But B is a very particular statistics. Right? For every statistics of B, you get a different characteristic. For example, you have a measuring device, and you can measure the crystal with many, many impurities, or you can measure crystal with less impurities. So apparently, the characteristics between these will be very, very different, because it depends on the statistics of B. Remember, it's S of B minus S of B under A. But what if you want to characterize a procedure, a measurement itself? Or, as Shannon asked, I can transmit stock market data, or I can transmit literature, poetry. It's a very, very different statistics of input. For example, which entropy is less? Well, you take William Shakespeare, and you take a telephone book in English. Which entropy is less?
Shakespeare.
Of course. Why?
There's context.
Huh?
There's context. The words have to.
There is a lot of correlations. And any poetry, of course, poetry is made up to, it's a mnemonic device. It helps you to predict, right? Because what poetry? It creates a beat. Okay, so you know more or less how many syllables in every sentence, and it creates rhymes, which is also a huge mnemonic device. Okay, and so again, But then you want to characterize not what you transmit, namely poetry, Shakespeare, or telephone book. You want to characterize your telegraph. Okay? And for this, Shannon suggested a quantity with which we'll be working, and we'll see in how different contexts they appear. And this quantity is called capacity or channel capacity. And that's what we want. So how would you characterize the characteristics of your channel itself, which would be not kind of to bees? First of all, it's clear that the mutual information is really how much information we obtain. But the mutual information depends on A and B, right? So capacity is defined, Shannon. How you would get out of mutual information? What would be your suggestion?
Can you repeat your?
You want to characterize the channel, your measuring procedure. Okay. So on some crystals it works better than on other crystals. Or you want to characterize your telegraph as a transmission. Okay? It transmits, highly correlated sequence with this mutual information and less correlated system with another mutual information. Okay? But generally, you are now not interested in sources, in bees. Okay? You want to somehow kind of, but you cannot average over all bees, right?
Normalize.
That's how actually science is done. Or in this case, it's mathematics, but then it turns into engineering immediately. So you need to decide what would be useful characteristics. You can define it as averaged over all possible statistics of B. And then you realize that maybe for many statistics of B, which is a statistic, which means that the statistics does not have its own statistics, right? So you just need to take every possible source. And then you realize that in many cases, the mutual information will be very, very low. So Shannon decided, and I'll show you in the next lecture, that it's really useful definition. It could not be right or wrong, right? It's your definition, right? It could be useful or useless. That's what is criterion for definition. So here you why the useful characteristic of a channel is called channel capacity, and it's a maximum of all possible statistics of an input, and it characterizes my transmission channel. That's the end of lecture, and if you want, think about why this is used, not an average. Well, you can take a minimum, which will be most likely 0. You can always find something for which your procedure does not work, or you can find average, which is not clear how. But you can find maximum. Maximum means that if you really want to use your channel very effectively, you can find yourself the statistics of B. For example, if you want this channel to work without errors, you can choose the statistics of B so that you don't use all three of this, you just use one of them, or you use this one of them. Then you have a perfect error-free transmission, right? You can always, but that means that you yourself choose an input. That's a motivation for defining capacity in this way. Okay? Tomorrow we'll have a tutorial, and it will be different from the tutorial like that, because I'll solve you a couple of problems from the book, and that will be on the exam. So it will be a little bit less technical and maybe a little bit more useful. Okay? 3:15 over there. Okay.
אפילו דוגמה של דוגמה של
Factorial they don't because they don't have the any significant factorial is from the book.
הפונקציה שלי זה פשוט money to one, כאילו אם אני באחד מהמחזורים האלה, אני רוצה את זה,
From your science, when we think about
בוא נעשה את התרגיל של האנטרופיה.
energy available to do
אז לפני שאני מודד, כאילו,
do mechanical work.
זה התפלגות אחידה
If
בין
you look at
המצבים,
the
אז
form,
זה
the
אוקיי, לא אוקיי.
mathematical formalism, then you
אחרי שאני מודד,
instead of energy you have some
לא, שני
average
מדדתי, אני
function
יודע
over
שיש
your
כאילו,
variable. So if say I don't know,
Yeah.
you have a neuron and you record you have an average firing rate. So
אחרי שאני מודד,
you
לא משנה
infer
איזה,
the Boltzmann distribution of this neuron and you build
איזה
the free
נאי
energy.
מדדתי, אני יודע שעכשיו יש לי ולוחות בין אין מצבים.
What does it
מדדתי
mean
את
in
זה, אני
the
יודע
case case? Only you know the
או
way.
זה או זה או זה.
The most general way that I'm looking at free energy.
האנטרופיה שלי תמיד אין.
Recently, in the last part of the course, it will